Hello, and welcome back to the Crunch stage. We are about to start with the second talk of today. And I'm excited. If you can hear my voice, make your way to the stage, find a seat. We've got seats up front, so no need to stand. As I'm sure you all are aware, we have Slido for the Q&A and for the feedback session, so you can go to slido.com and use hashtag CrunchConf to submit any of your questions you would like to go through at the end of the talk, and you can also submit any feedback you have about the talk. And now, I have nothing else to do but to introduce the next speaker. She is an electrical and biomedical engineer specializing in machine learning and computer vision. Please welcome Irina Vidal Migallon to the stage.
Thank you. Hello, everyone. Thanks for joining. I'm very excited to be here today. It's a beautiful venue, so thank you all for joining. So I'm going to have a feel for the room. Who's working in computer vision currently? Show of hands. OK, a few hands. Are you already familiar with adversarial examples? No? A few hands went up. OK. So we're actually going to be talking about that, about what exactly they are, how they affect you, if you should care, and in the case that you should care, how you can actually use them to improve, to break, and then improve your computer vision models. So just to get everyone on the same page, I'm not sure if you've seen this image. It's the stereotypical image that we can see for adversarial examples. It comes from the Ian Goodfellow paper from 2014, where he and his team were explaining one of the most basic attacks that you can make against computer vision neural networks. What they did was they took an image of a panda, amongst others. They slightly perturbed them in a way that humans wouldn't really notice, but yet the neural network that was at the time classifying this image was thrown off and would say, instead of a panda, they were seeing a gibbon, which of course we can see in the image. It looks nothing like a gibbon, right? Now, a few things have passed since, and another team has transferred these kind of attacks to the physical world. So now they're not just able to perturb digital images, but actual 3D objects. And what you'll see in the video is how the original 3D object that was printed of a turtle, the original one is correctly identified as a turtle by an inception model. However, when they perturbed it, they were able to 3D print that adversarial 3D object in a way that it was consistently identified as a rifle by the classifier. Now, if you can think of all the implications that this might have in different systems around the world, well, it's quite mind-boggling. Now, why do I care about this? You've heard, I'm a computer vision engineer by trade. I've been working in applied research in healthcare mostly. That's where my background lies. And more recently, I've been working in autonomous mobility. Now, other than surveillance systems, healthcare and autonomous vehicles are two of the domains where adversarial examples are going to have a huge impact. And that's why I'm so worried about them, or at least I care so much about them. Now, what exactly is going on behind these examples? What do we mean when we say adversarial? It means that it's not just a mistake, it's not just an error that happens in your neural network model. It means that someone has actively designed a sample of your data to break your classifier, your detector, your computer vision model. So what's going on is, for instance, you can see an example here applied to autonomous mobility. This was a team that were able to perturb traffic signals. And what you're seeing here is a stop signal where they applied stickers that could pass as some mild vandalism, in a way that when it went through a classifier, instead of seeing a stop signal, it was identified as a 45-mile-per-hour signal. Now, imagine the effect that might have in autonomous vehicles. But if you're thinking that that just applies to classifiers, think again. So this other team
we're able to transfer this to a detector. If you've heard about YOLO, it's one of the most popular detectors out there. YOLO V2, in this case, what they were breaking was the YOLO V2 detector. And in fact, you can actually see it outside. There's a company that has a booth with this running online constantly. What this team was doing was they 3D printed a poster that, when held in front of a person, would completely hide them. And if you can see in the video in a couple of seconds, you'll see how when they turn around the poster, they are again detected correctly. And when the poster is passed to the colleague beside them, the colleague gets hidden. So again, think about surveillance systems, and if you care about your privacy, then you might want to get a t-shirt wearing this poster. Now, you might think that, well, for autonomous vehicles, we're fine, because unless you're Tesla, you're going to be equipping your vehicles with not just RGB cameras, but LiDAR systems, right? However, this year at CVPR, we saw another team who were able to also fool point cloud detectors. So what you're going to see in this next video is the expected behavior. To the right, you'll see the RGB image. To the left, you're seeing the point cloud. You're seeing the LiDAR. And you'll notice how when the vehicle approaches a benign 3D object, it's correctly highlighted. You'll see a cube highlighting the object. Now, in the adversarial example, when they 3D printed an adversarial object, this doesn't happen. Notice how to the right of the vehicle, you'll see a human that is eventually detected. However, the 3D object is not. And you can see how the vehicle approaches that object without seeing it at all. Now, again, this has huge implications in autonomous mobility. And my last example for the day applies to healthcare. So I was saying that this doesn't just apply to surveillance and autonomous mobility. This year also we saw another team who were able to replicate these attacks on healthcare images. In this case, you're seeing a benign mark that got incorrectly labeled as a melanoma. And the same team applied it the other way around. So they took an image of a melanoma, slightly perturbed it in a way that I'm going to explain to you in a second, and got the diagnosis that it was perfectly benign, which was incorrect. They also applied it to pneumothorax images, by the way. Now, what's going on here? We can simplify this to get an intuition of it. If you think about it as in two features, in our feature space, we've got a decision boundary that we're going to be using to tell if a sample belongs to class A or class B. And what an attack tries to do is take a sample from class A and perturb it with the minimum energy possible so that it goes over the decision boundary and gets classified as class B. That's what we're trying to do with an attack. Slightly move our samples to the feature space that gets classified as class B. Now, there's several ways to do this, and the most simple of attacks actually seems very similar to the way we train neural networks. So if you're familiar with them, you'll know that what we usually do is you take a bunch of images, you put them through a classifier, and for instance get the classification, and when it's correct, for instance an image of my laptop will give the label laptop, and when there's an incorrect label, there will be a loss that goes up, right? We can take that loss, we take the gradient of that loss with respect to the weights, and that's what we backpropagate. So you've probably heard this a bunch of times. Now, the big difference between how you're training your neural networks, where you're tweaking the weights with that slight gradient until the loss goes down, and an actual attack is twofold. In an attack, one, you do not want that loss to go down, right? You want to maximize that loss. You want that error to go up. And two, you've already trained your model. We are attacking an already trained model, so we're going to see it as something frozen. And so what you actually do is you take the gradient with respect to your input image instead of the weights. Because what we're going to be tweaking is not the weights, but the input image. So that's what you're seeing in this photo right here. you're seeing that that perturbation, that apparent noise, which is not noise at all, it's actually the gradient of that loss with respect to the input image, and that's what we can then add to the image to generate our adversarial example. So this is one of the methods. We'll see ways of using it in a second. Now, all of these attacks, we can classify them in different ways. We can look at them with respect to, for instance, how much we know about our target model. On one of the spectrum are black box attacks, where we know absolutely nothing about our model. We don't know the laws, we don't know the data that was used to train them, we have no access to the weights, we know absolutely nothing. We can just prove it. On the other end of the spectrum, we have white box attacks, where we know everything about the model. We can even use the loss to optimize our attack over that model. And somewhere in the middle are attacks that, for instance, have a proxy model they can optimize on to attack the real system that they're trying to attack. Another way of seeing them is what we're aiming to get. What kind of effect do we want with our attack? Now, I just showed you the video of the team that produced a poster to hide a person from surveillance systems, right? So one way you can achieve that is by lowering the confidence of a prediction. Most computer vision systems have a confidence threshold, right? So when you have a prediction saying, well, there is a human in this position, you also have a confidence that that human is there. If you're able to reduce that confidence, the system will probably disregard that prediction as a false positive. So the mildest of attacks is just reducing the confidence of your predictions so that they get dismissed. The next level up in harshness of your attacks is managing to get the wrong prediction. So like in the case of the turtle, or like in the case of the stop signal, if we get the wrong prediction, if we get, well, this is not a turtle, this is a rifle, or this is the wrong kind of digit, this is the wrong kind of object, we're already breaking the system. And an even harder attack is where we know exactly the label we want to get out of the system. So for instance, if you want to forge a document, if you wanted to read 900 instead of 100, I mean, if you're writing a check, who knows, you want to tell the system, well, this one, you're going to be reading a 9 from it. And that is a targeted attack. And in fact, some of the papers I've presented before were doing that. We're choosing a specific label, and we're saying, instead of having this turtle, you're going to always say rifle. Now, those are the different types of attacks you can have. But why are they happening? And here I've got bad news, actually, because there is no consensus in academia yet. There's been a lot of very reasonable hypotheses, ranging from, well, maybe neural networks are still too linear. Even if they have nonlinearities, they are too linear. Maybe we're moving in high-dimensional spaces, and that's why we see these problems. Maybe they are overfitting on certain features. But more recently, actually, a few months ago, there was a hypothesis that got me extremely excited because of the implications it has. A paper by Adversarially and colleagues proposed that actually what we saw in adversarial examples are not bugs at all, they are features. Meaning, what we're seeing is neural networks focusing on features that humans cannot see at all. And they were able to disentangle what they called robust features from vulnerable features. Meaning, there are features that the neural networks see, and that when they get perturbed, they produce a huge impact, but humans are not aware of them. So I'm going to try to give an intuition of this. And you're going to, if you want to participate, I'm going to ask you to behave as those humans that cannot see all of those features. So let's take this bunny. Well, first of all, are we all seeing a bunny? Show of hands. Is this a bunny? Okay, we're on the same page. So let's imagine that humans, that we can only have two features again. Let's say we have an outline of an image, and we have the content. Those are two separate features. Now let's say neural networks are able to see the full image, but humans cannot. Humans can only see the outline of an image. So as humans, you're only able to see this. So I'm going to ask again, is this a bunny? Who sees a bunny here? Okay, we're still seeing bunnies. That's good. Now, what this team means with robust features is this. So we can perturb these features in a lot of ways, and as long as we have the fluffy ears, the head, we can still see bunnies everywhere, I think. Are we still seeing bunnies here? Okay, good. Then what if I start perturbing even more the image? We can still see that rough shape. Now, this is what humans are seeing. What if I perturb the content of the image? Humans are not able to see it. Humans, I suppose, are still seeing a bunny here. But what a neural network sees is this. Are we all seeing a bunny? Who thinks this is a bunny? Absolutely nobody. Because I've changed the features that the neural network sees. Of course, this is all simplified, but this is the point of the matter. There are features that humans were not seeing because humans were only able to see the outline. For a human, that is still a bunny. However, the neural network is able to see the content. And I've only added a slight layer on top of that bunny face. But that's enough for you to say, well, no, this is no bunny at all. This looks nothing like a bunny. And that's exactly what was going on in the image from this paper. One thing is to focus on certain features that are very obvious to humans, and we can perturb them to a certain extent, and we will still see what the object is. But there are some features that are possibly only seen by neural networks that are also highly correlated to each of the classes, but humans aren't seeing. So a slight perturbation of that, let's say in the texture, to us means nothing, but to the neural networks, it means absolutely everything and means them saying, well, this is not a frog anymore, this is something else. Or, like in the case of the bunny, no, wait, this is not a bunny anymore. Now, should we be caring about this? Because this is fun, this is actually a lot of fun to look into, but we've got a lot of work to do when we're designing neural networks, right? When we're designing a computer vision model, we need to think about how we're going to be collecting our data. We have to think about actually deploying a team to go to the field and collect the data, or maybe if you're working with autonomous vehicles, you need to make sure that all of those images that they're collecting while driving around, that you get them back. Then you have to get them probably to an annotating company, or maybe you have people in-house who are annotating them. You have to think about how you're going to be training your model, the right augmentations to it. You have to have a proper evaluation in place. And before you deploy that to production, you need to stress test your model. So there's a lot of work to do, right? And that means experience, that means diversity so that no mistakes are made, that means a lot of time, so basically that means money. And we don't always have that amount of money to do things properly. And when we don't, well, things happen. And then there's this quote going around that you should never attribute certain things to malice when you can actually explain it through stupidity. And when I say stupidity, I'm actually meaning that lack of experience, of diversity, of time, of money. And when we don't have that kind of resources, things happen. So we've seen in the last few years some huge problems caused by computer vision models deployed. We've had systems that were predicting how likely a person was to commit a crime again, who were extremely biased against black people. We've had systems who were deciding how adequate people were for roles, who were biased against women. We've had a few accidents from Tesla and Uber where lives have been lost. And those were not caused by hackers. Those were not adversarial examples. Those were mistakes somewhere in the chain between the design and the deployment of a system. Those were not intended. Nobody set out to actually attack the system that way, and yet these happened. So what I would argue is we do need to care about adversarial examples because possibly, maybe, eventually, our systems will be targeted and they might make us fail. However, we've got a lot of work to do to cover the basics because those failures will make us go down a lot faster than a hacker would. Now, let's say you realize that you still have to care about this, you want to be prepared, you want to robustify your systems against these kind of attacks. How would you go about it? Now, let's say we've got covered data collection, the annotation, our evaluation. Well, ways that adversarial examples can help us are mostly while training, so while we're augmenting, and two, when we're testing. So they are extremely useful to stress test our systems. So when you're training, if you're working on computer vision, and I saw a few hands going up, you're probably already augmenting. You're rotating your images, you're flipping them when it makes sense, you're adding true noise to them, not adversarial perturbations, you're playing with intensity values, with contrast, so you're probably applying a lot of augmentations to your training data to robustify your models already. Now, if you think about it, adversarial attacks can be an extension of that. You can simply start producing those adversarial examples so that while you're training, your system sees them and gets ready for what might come. Now, the way this would look is you have your original training data, and you have a toolbox that can produce adversarial attacks. So you insert that data into your adversarial toolbox, and you end up having a ton of adversarial examples on top of your vanilla training data. You feed that into your neural network, and ideally, you end up having a more robust model. Now, the problem with that is that, well, there's both the pro and the con is exactly the same thing. It's fairly agnostic to the reasons behind adversarial attacks. You don't have to care about why exactly these happened. You don't have to care about whether they are features, bugs, if the problem is nonlinearity or too much linearity. You don't care. It's a brute force approach. You just have to start feeding your model with more and more adversarial examples, hoping that it will pick up on what matters. The problem with that is that you're learning nothing. You don't really know when to stop. So you keep throwing things at your model, but when is it enough? You've got no idea. Now, a way to go about that is through testing. Especially if you want to get your model certified, you may want to know exactly where you are with respect to models and with respect to attacks. So again, you start with your original data, your testing data, and an adversarial toolbox. You feed it in, you end up producing your adversarial examples on top of your testing data. And in this case, what you're doing is you feed it to an already trained model, because by now we're done training. Our trained model is there, we freeze it, and we're just feeding testing images to know what's going on. And so the result is you can say, well, we are immune to attack X, we have this kind of robustness against attack Y, and attack Z completely broke us. So perhaps your model is not extremely robust, but at least you know exactly which ones are breaking your model. So if you're extremely systematic with respect to what attacks you're sending your model, then at least if there's an authority certifying your model, you're able to explain to it where you are immune and where you will most likely fail. So knowing where you're at is already extremely useful before you deploy to production. Now, there should be a little plus to it. There should be a little more something a little better that you throw in there. And those are interpretability tools. So there was a workshop a couple of days ago precisely talking about this, about all of the different tools that you can use to explain your models. And testing is a very good moment to do just that. And the way you would apply it is, so if again I take the image of my laptop, if you remember, I applied that initial attack on it, producing a perturbation, I added it to my original image and produced the adversarial laptop, so to speak. In this case, the basic of testing would say, well, I've got my adversarial attack, I fed it into the neural network, and now it says that it's a prayer rug, that my laptop is a prayer rug. You could stop there and say, well, I completely failed against the fast gradient method. Okay, that's step one. Step two is saying, okay, what is my model looking at when it looks at this adversarial sample? Because if one of the possible explanations was that neural networks pick on features that I'm not seeing, I should be able to probe it and ask it, okay, what are you looking at when you see my images? And there are tools that can help you do that. So if you use tools like Lime or SHAP, you're able to do what's called an occlusion sensitivity test. So you feed your network and you take a look at what the model is focusing on when it's making predictions. You can see here how when I feed my original image and I get the correct prediction of a laptop, the model is focusing on where any human would look at to identify a laptop, right? However, if I feed it the adversarially perturbed laptop, what you can see there is that the model is focusing on all the wrong areas. So now we understand that the model isn't buggy. The model isn't just random, it doesn't have random weights. What it is focusing on the wrong areas of the image, because what should be the main object is just not representative enough. The features are not enough to make it focus on them and say, this is a laptop. So this is how we see why the model thinks this is a rug instead of a laptop. Now, there's a bunch of tools that you can use out of the box for this. Clever Hands has been around for a long time. It's linked to Goodfellow as well. I would really suggest that you take a picture of this and try a few of them and see which one works for you, depending on the framework that you're specialized in. But basically, what this does is it gives you a huge list of attacks, of known attacks, where you could just import it. You pip install these tools, you import the attack that you want to apply, and you start producing your adversarial examples, whether for training or for testing. However, if you want to tinker, the most basic of attacks is right there. That's the fast gradient method. So of course, I'm leaving out all the parts where we're actually feeding the images through the attack, but that's the fast gradient method right there. It's just 10 lines of code. So I'm leaving there a couple of links to either collabs or a tutorial, in case you want to tinker yourself, which is a lot of fun, and start feeding images of your laptop or your mug or whatever and see what it returns. This is where you can start. Okay, so this has been a bit of information up until now, but the best part is actually your questions. So thank you very much for your attention, and let's take a look at Slido and see if there's any questions from you guys.
I can. So shouldn't we distinguish between compass system and the other two examples? There is a difference between shady business and mistakes.
So definitely, adversarial examples are I assume what you call shady business. That's why we don't call mistakes adversarial examples per se. You can bootstrap a system by collecting your mistakes and feed it again to your system, but those don't really count as adversarial examples. Adversarial examples are explicitly samples that are crafted to break your model. So I'm guessing that's the distinction you wanted to make.
How do you constrain the amount of change applied to the input when you are using gradient descent?
Right. There's a factor I didn't include in the images, but for instance, in the case of the fast gradient method, there's always an epsilon. So you get the basic perturbation, and then instead of completely adding it to your image, you tweak it through a factor. It's just a multiplier. On top of that, there's other methods that are iterative. So the fast gradient method is just one step. You take the gradient, then you tweak it through the epsilon. However, there are other methods that are iterative, and you can tweak how many times you're going to go around to optimize that attack. So it is tweakable.
So MJ is wondering, can someone create adversarial examples having zero knowledge about the model? Total black box environment.
Oh yeah, definitely. That's, if you want, that's the scary part. It just depends on how much money you have, actually. But there's a lot of literature that you can look into. There's a lot of people who are taking APIs, like the one from Google. There's several companies out there that offer computer vision as an API. You just query it, and you get a response of what is in your image. And they say, I have a budget of N,000 euros, or maybe less, and I'm going to just probe that image, probe that API, and you get a response. And it's been proven that all you need is enough queries to end up crafting an attack that breaks them. So it has been done. Yep.
That is kind of scary. Is it possible to measure, quantify a neural network's vulnerability to these kinds of attacks?
It is. What metric you use is up to you. So there's, again, a lot of literature defining metrics that describe vulnerability, or on the other side, that describe robustness. It's a very mature field, so different metrics are coming up every day. But a very basic way you can define it is, well, I've got these attacks, I'm going to craft these many adversarial examples, and this is the percentage I get of failures or successes of my system against those adversarial examples. But again, there's a lot more to it. There's a lot more metrics that we can look into. There's a lot of literature on it, depending on what you want to focus on.
Matt is wondering, does your talk also apply to non-vision data?
Oh yeah, and definitely. So I focus on computer vision, but there's a lot also in NLP, structured data. There's other domains in speech, for instance. There's also such cases in speech. Basically, any machine learning, and in fact, this doesn't just apply to deep learning. In fact, deep learning is a lot more robust to it than traditional machine learning. So any domain you can think of has adversarial examples, and any technique you can think of is fragile to it. So a linear regression, incredibly fragile. It breaks like that. Neural networks are a bit more robust, but still you've seen how it can be broken. But if you're curious, you can look up adversarial examples for speech, for NLP, for basically anything you can think of.
So far, the examples all worked by adding noise to images. Couldn't we just always denoisify input images, both in training data and new data? Yeah,
that's a really good question. You could, I was about to say theoretically, but not even that. When you denoise, so basic computer vision, when you denoise an image, what technique do you apply? It's not that simple, right? You could, one way of doing, so one defense that initially they were doing, for instance, against a fast gradient method is you just rotate your image slightly, you perturb it when the input adversarial example comes, and that usually is a defense that is strong enough. However, we're beyond that. Now all of these attacks have been exported to the physical world because they are robust to these kind of perturbations. So that's a no-go. As for denoising, how exactly do you need to denoise it? Smoothing isn't just enough. So the technique that you choose is not going to be enough to these, especially if it's an attack that has already been transferred to the physical world. So, and that's the thing. Of the examples that I showed, some of them indeed were based on digital image to which we overlaid some perturbations, so not noise, perturbations. Now, some of those have already been transferred to the physical world. The turtle, it was in the physical world. It was robust to all those kind of rotations, flipping, anything you did to it also worked. And that includes adding noise to the sensor. So sadly, it's not enough to just
denoise the image to hope that you're robust. That's just not enough.
I think we have time for a couple more. So how long compute time does it take to generate an adversarial example, like the one with your laptop and the rug?
Oh, it depends on the GPU. On a K80, it took 400 milliseconds. So it's fairly fast to do. And in fact, you can also try it on the CPU. It's not exactly efficient to do it on a CPU, of course, but it's definitely under a second. It's half a second for each example. So if you consider it in a testing scenario, you can perfectly do it. It's something that is fast enough to apply.
Also kind of scary. Do you think that we will be able to create a model as robust as a human eye or brain at some point?
Actually, we're beyond that. Many computer vision systems are more robust than humans globally, in the sense that we need to account for humans that sometimes are tired, they are bored, they lose focus. So there are many tasks where computer vision systems are already better than humans. For instance, in healthcare, we usually are not allowed to say that. The FDA doesn't look kindly upon systems claiming to do diagnosis better than humans. But technically, we are very close, if not beyond that. And again, if you take into account all those cases where humans are just not paying attention because life happens, your body gets tired, your mind is elsewhere, computer vision systems are already, for many cases, better.
I think that's all the time we have for the Q&A here. But if you would like to find her afterwards, she'll be around the Prezi booth. Please, thank you very much for the talk.
Thank you.
And now we have a short sponsor video, and then we will move right into the next talk, so stick around, but enjoy the video.